All right, here's another video dealing with the evaluation theorem. I wanted to come up with 3 examples just because it felt right to give you some examples before we left this section. But I think what you'll find is the examples in this section aren't all that different from the examples in section 4.8 when we learned antiderivatives. Really, most of the work with the evaluation theorem is just can you figure out the antiderivative? And if you can do that, well, then it's easy. Plug in a couple numbers, refer to your calculator, do whatever you got to do to get the final answer that you put in. Without further ado, what if you were asked to find, let's see if we can translate this into English, how much area is there under the curve y equals sine of x from 0 to pi? You certainly don't need a graph to answer this question, but just if it helps you to have a picture to look at, what we're asking is how much area is there right here? Right, here's the graph of y equals sine of x. It starts out at 0, and then it gets back down to 0 after it travels a distance of pi. And then when it travels a distance of 2 pi, it kind of repeats. So it picks up doing here the same thing that it was doing right here. And I don't know, I'm kind of curious how much area is there right here? I mean, I know this height right here is 1, but how much area is there? I have no idea. Like, it's not a rectangle, it's this weird curve. Well, this will figure it out. All we need to figure that out is to know what the antiderivative of sine of x is. Well, fortunately, we know what the antiderivative of sine is. And you're like, oh yeah, it's cosine, right? Careful here, it's not. The derivative of sine of x is cosine of x. But the antiderivative of sine of x is actually negative cosine of x. And that's because the derivative of cosine of x is negative sine of x. So we need this negative here so that when we take the derivative of this, we end up with a positive sine of x. Anyways, the antiderivative of sine of x is negative cosine of x plus c. You don't have to write the plus c because we're trying to evaluate a definite integral here. So we're just going to make clear to the reader that we need to evaluate this from 0 to pi. And that's easy enough. I just need to know what is the negative of the cosine of pi. And then once I figure that out, I can subtract the negative of the cosine of 0. These might be more steps than you need to show, but I'm just trying to show as much as I can to help people follow through this. Let's see, the cosine of pi. In case it helps, here's a unit circle. Pi is over here on your unit circle. Remember, 2 pi goes all the way around. And maybe you remember, I know it's been a while, that the cosine is always the x-coordinate of that point on your unit circle. So if you think in terms of x's and y's here, to get to this point, it's at -1 is your x value. The y value is 0, although that's not relevant. So what I'm saying is the cosine of pi is -1. So we have the negative of -1 here. And then we have to subtract from that the negative of the cosine of 0. Well, cosine of 0 is talking about the x-coordinate of this point, which is exactly 1. So I have the negative of 1. And so let's see, what does this all evaluate to be? The negative of -1 is +1, and then minus another -1 is plus another 1, so I end up with 2 here. Maybe that's interesting. The area right here is 2. Go figure. I wouldn't have guessed that. I don't know. I mean, these different heights, root 2 over 2 and root 3 over 2 in here, and this is a distance of pi, an irrational number. It's kind of interesting, maybe, that this area right here is 2. Here's something that I think is interesting that probably doesn't deserve its own example, so I didn't make an example, but I figured I'd talk about it. We haven't decided how we're going to deal with area below the axis. When I talk about 2 here, I'm talking about the area above the x-axis. I'm talking about the area of this kind of region in here. So what about down here? What's this area? Well, it turns out we're just going to define that area as negative. And due to the symmetry of this graph, we'd expect this to have an area of -2. And I can kind of show you how this has an area of -2. We could do it a couple ways. We could do this same example, except evaluate it from pi to 2 pi. Right? And that'll give me the area from here to here, and I'd expect the answer to be a -2. Another way you can get there is if you evaluate from 0 to 2 pi the integral of sine of x. So essentially what this is saying is how much total area is there from here all the way to here. Well, we already know this is 2, and this should be -2. I'm expecting the answer here to be 0 if I do everything right. Well, I can kind of cheat a little bit. The antiderivative is still negative cosine of x. It's just now I have to evaluate it from 0 to 2 pi. And so 0 and 2 pi, they're both talking about this point right here. The x value at this point is going to be +1. So what I'm going to end up with here is negative +1 minus negative +1. I'm going to get -1 plus 1. I'm going to end up with 0. Oh yeah, I knew that was going to be 0 because the symmetry of the sine graph tells me there's as much negative area from 0 to 2 pi as there is positive area from 0 to 2 pi. Anyways, I think that's interesting. Maybe you don't. Here's another example. Here we have the definite integral of 3 divided by the square root of 1 minus x squared, and we're evaluating it from negative root 2 over 2 to positive 1/2. This can look really intimidating. This can seem kind of scary, until you recognize that, wait a minute, 1 over the square root of 1 minus x squared, that is just the antiderivative of arcsine. So if I pulled this 3 out in front, I could say this is 3 times the definite integral from negative root 2 over 2 up to positive 1/2 of 1 over the square root of 1 minus x squared. And then I can kind of save the 3 for now and just deal with all this stuff, right? The integral of 1 over the square root of 1 minus x squared evaluated from these endpoints. And since I know the antiderivative of this thing is arcsine, all I need to do is evaluate arcsine of x from negative root 2 over 2 up to positive 1/2. Some people put parentheses here. I kind of feel like you should. Some people leave these parentheses off and kind of let this be the thing closing these parentheses. I don't know. To me, that feels inconsistent because like right here, I didn't put parentheses right here. So I usually close the parentheses here just because it bugs me to not do it. But either way is totally fine. At any rate, I have 3 times something. Remember that what this notation inside the parentheses means is change all the x's into 1/2 and then subtract what you get when you change all the x's into negative root 2 over 2. So I got the arcsine of 1/2 minus the arcsine of negative root 2 over 2. How good are you with your arcsines, right? It's probably been a little while. There's no reason you should remember this unless you teach math for a living like I do. Arcsine is a function that's defined from negative pi over 2 to positive pi over 2. It's kind of defined in this region over here. And what it's asking you is what angle leaves you at having a sine of these values. Well, sine on your unit circle is always the y-coordinate. So this is just asking me what angle in between negative pi over 2 and positive pi over 2 will give me a y value on my unit circle of positive 1/2. Well, positive 1/2 is talking about this point right here. And you may remember that this point right here corresponds with a 30-degree angle. Although what you'll see is anytime we're dealing with inverse trig functions, we're going to deal in radians instead of degrees. So instead of calling this a 30-degree angle, I'm going to call it pi over 6. Similarly, this is asking me to find the arcsine of negative root 2 over 2. It's saying where in this region am I left with a y-coordinate of negative root 2 over 2. Well, negative root 2 over 2, you might remember, is kind of the point that's over here. This is a negative 45-degree angle, or in radians, it's negative pi over 4. So I want, be careful with your signs here, to subtract negative pi over 4. All that's left now is to kind of add and subtract some fractions. Let's see, we have 3 times pi over 6 plus pi over 4. I guess I could call this 4 pi over 24 plus 6 pi over 24. And the negative and a negative make a positive. And then 4 pi and 6 pi give me 10 pi. And then this 3 and this 24, I could cancel out and make it 10 pi over 8. Because 3 divided by 24 is the same as 1 divided by 8. And then this reduces to just 5 pi over 4. One more example, then we'll call this video good. Stare at this thing and you're like, oh, let me stop you. I got this. You're trying to make this really hard, but I can kind of see your arctangent thing going on here, right? The 1 over 1 plus x squared. Okay, first off, good job recognizing that if you recognize that. But second off, no, actually, this doesn't work. This is kind of the reciprocal of that with an x floating around. This is meant to kind of sort of look like that and give the student the idea that, oh, maybe I have to do some crazy algebra to get arctangent out of this thing. You don't. What you want to do is algebraically simplify this thing, and I think what you'll be able to do is algebraically simplify it so that it's just a sum of powers of x. What I'm saying is this is the integral from 1 to e of, anytime you have a sum of things divided by x, you can rewrite that as the sum of each of the things individually divided by whatever the denominator is, x in this case. Right? And if you have a hard time going from here to here, remember that if I started you out in this case, you'd be like, well, you got a common denominator. So all you got to do is add up the numerators and write that all over your common denominator. Right? It's the same reason 1/5 plus 2/5 is 3/5, is why 1 over x plus x squared over x is 1 plus x squared over x. And if green is the same as red is the same as green. This is a useful little algebraic technique. Anytime you have multiple terms divided by a single term, you can write that as we did here. And the advantage to this form is I can simplify things a little bit, and then I'll be able to take the antiderivative. The 1 over x is already good. I already know that antiderivative. This one, x squared over x, there's no like quotient rule for antiderivatives. What am I going to do here? Well, you can just simplify this, right? And x from the top and the bottom both cancel, and we get here. And again, if you want to put parentheses around this because it makes you feel better with this dx, feel free. I don't bother. All right. Antiderivatives of this guy. The antiderivative of 1 over x, be careful, you can't use the power rule there. This is the one where it's the natural log of the absolute value of x. Over here, you can use the power rule. Think about this as x to the 1 power. So its antiderivative would be 1/2 x to the 2 power, or x squared. And I got to evaluate that from 1 to e. First, we'll plug in all the e's. You kind of always plug in the things on top first. So this is going to be the natural log of the absolute value of e. The absolute value of e is just e. Plus 1/2 e squared. And then when I get that answer, which doesn't need to be in parentheses, I just think it makes it more clear what you're doing. I want to subtract what I would get if I plugged in 1's into that same expression. So the natural log of the absolute value of 1, that's weird looking, plus 1/2 times 1 squared. Let's see how well these work to evaluate. The absolute value of e is just e. The natural log of e, you might remember that from a, Algebra 2 class, pre-calculus 2, whatever you call it. That's equal to 1. And that's because the natural log is just asking you to what power must you raise e to make it equal to whatever you wrote right here. So I'd have to raise e to the first power in order to make it equal to e. Anyways, 1/2 e squared, nothing much I can do with that. I'll just call it 1/2 e squared. And then from this thing, I want to subtract the natural log of the absolute value of 1. Well, the absolute value of 1 is just 1, and the natural log of 1 is 0. Why? Again, the natural log is asking you the question, what power do you got to raise e up to make it equal to 1 in this case? Well, e to the 0 power is 1, right? Anything except for 0 to the 0 power is equal to 1. So the natural log of 1 is just 0. And then 1/2 times 1 squared, well, 1 squared is just 1, and 1/2 times 1 is just 1/2. So I get this, and I guess I could say that the 1 minus the 1/2, because remember I'm subtracting both of these terms, gives me 1/2. And then I have the 1/2 e squared. And if you think it's prettier to write it as 1 plus e squared over 2, you go right ahead. Whatever you like better out of the two of these is totally fine.